So I come back to this. I wanted to spend just a minute or so just to introduce our three speakers, Megan, Maité, and Faith. So I'll tell you a little bit about these students as well, because it's been an honor working with them. Actually, Megan, all of them are from Georgia Tech. They have a tremendous experience doing work, in their own disciplines. And then they took on this project and trying to help us. And they'll tell you a little bit more on how to, understand at first and simplified models. How do we understand function in the brain, and can we model it in the brain as we're doing brain surgery to be able to stimulate? They are extraordinarily accomplished, as you can see, in their CVs. They're really at the top of their class, and they're extraordinarily bright and energetic. Maite is also same deal, extraordinarily accomplished in their work with multiple honors, and really, really a pleasure to work with them this last semester. And Faith, they just really continue to just push us beyond our area of expertise. And you'll see the kind of work that they are going to be presented, which is a 3D printed surgical stimulation tool for brain mapping, training, and preoperative planning. So I stop right there. I'm going to stop sharing right here so I can let the students, I think that they have their own presentation. Megan, I see you smiling right there, and Faith and Maite, I think that you guys are, so why don't you guys take it away? So we have about 30 minutes, and that way I know that you guys are very efficient, and we're very excited to have you guys this morning.
Thank you so much, Dr. Q. I'll share my screen for our presentation for you guys today.
Thank you for that really quick introduction, and we are very excited to be sharing what we've been working on with everyone today. My name is Maite, and I'm actually originally from Minnesota, right by the Rochester Mayo Clinic, actually.
My name is Faith, and I'm from Tampa, Florida.
And my name is Megan, and I'm from Philadelphia, Pennsylvania. So we're a group of recent biomedical engineering graduates from the Georgia Institute of Technology up in Atlanta. And we've been lucky enough to be in collaboration with Dr. Q and his team for about the last 6 months or so. We're really grateful to have the opportunity to be here today to share all of this with you. So Georgia Tech is actually one of the top ranked programs in biomedical engineering in the whole country. And one of the benefits that gives us as students is that there's a huge emphasis on team-based and project-based classes. So throughout our time as undergraduate students, we've actually been able to participate in a lot of design-based classes. The most senior of these is called Capstone Design, where we're actually given the task of designing a medical device in order to solve one of society's most pressing biomedical problems. So our specific project was actually sponsored by Dr. Q and his team from Mayo Clinic. With their clinical expertise and with our engineering and quantitative backgrounds, we are able to succeed in creating something to address a clinical need and the needs of the patient. So with that, we would now like to share our work with you, a 3D printed surgical simulation tool for brain mapping training and preoperative planning.
So as Megan said, our surgical simulator is used for cortical mapping, which is a neurosurgical technique that is used for intraoperative monitoring. As shown in the video to the right of the slide, you can see that this technique enables neurosurgeons to identify eloquent tissue areas that are responsible for motor, sensory, and language function, thereby enabling surgeons to avoid cutting into these essential brain tracts during neurosurgery. Cortical mapping is used in a variety of procedures, but for our capstone project, we focused on its applications with respect to tumor resection surgeries. This is an essential skill to learn to successfully perform these types of procedures and improve patient outcomes. The current training for this technique uses the phrase see one, do one, and teach one. This refers to the training methodology whereby neurosurgery residents observe an experienced surgeon perform the technique, practice on cadavers, and assist in the operating room, and explain the procedure to someone else. However, there are several drawbacks to this training methodology, specifically with regards to its reliance on cadavers. Cadavers are fixed post-mortem, and this process hardens the body's tissues, including the brain. Not only does this lead to inaccurate physiological conditions, including false haptic feedback, inaccurate material properties, and no blood circulation, but fixing the brain also inhibits its ability to respond to electrical stimulation. Therefore, it is impossible to learn the cortical mapping technique on cadavers alone. In addition, cadavers are expensive, unsustainable, and difficult to access around the world due to various ethical and religious beliefs. We propose to change the phrase for training methodology to see one, sim one, do one, and teach one, where sim one refers to practicing cortical mapping on a surgical simulator model. Surgical simulators have been proven to have translational value in a clinical setting, and skills obtained through practice on simulators can assist with performing associated procedures in the operating room. In order to help neurosurgery residents obtain these microsurgical skills outside of practice on a cadaver, the Mayo Clinic presented us with the challenge of developing an electrically functional brain model for surgical training. This is especially relevant now due to strict resident working hours and limited lab access because of the COVID-19 pandemic. In addition, the Mayo Clinic constrained our design challenge so that we were focusing just on cortical mapping with respect to intracranial tumor resections. To begin the design ideation process, 13 user interviews were conducted. These interviews consisted of 7 neurosurgeons, 5 residents, and 1 product subject matter expert. Our interviewees were employed by the Mayo Clinic in Jacksonville and Rochester, Emory University, and the Baycare Health System. These interviews were conducted with open-ended questions to help us best understand the needs and room for development in these fields. Using the input we received from these interviews, we developed a panel of critical product features. This is a common practice in engineering disciplines in order to develop quantitative tests to validate the function and performance of a device. The first critical product feature was electrical stimulation. The primary function of our model is to simulate the cortical mapping technique. So it was critical that our model could respond to stimulation just like live brain tissue does. Not only did we want bipolar electrode probes to be able to accurately detect and differentiate between various tracks, but we also wanted to establish a linear relationship between the placement of the electrode and the distance to the nearest tract. This relationship is what allows neurosurgeons to avoid cutting or damaging these important brain pathways during surgery. The next critical feature was elasticity. Elasticity was used as a quantitative measure of the haptic feel of the brain. We wanted to ensure that our model felt like a more accurate representation of live brain tissue than fixed cadaveric brain tissue. This would better mimic the state of the brain during an actual surgery. Finally, we wanted to accurately represent the cortical tracts in the brain. Due to time constraints, we chose to only focus on the motor tracts in the first iteration of our model that you will see presented here today. We wanted to place these tracts in the correct location, so we utilized the homunculus and patient imaging data to do so. After we established these critical product features, our team went through a lengthy concept generation process as a part of our senior capstone design course. We started this process by having each of our 4 team members generate 20 design concepts, bringing us to a total of 80 different ideas. From these ideas, we extrapolated our top 4 engineering design needs, which were tract representation, signal decoding, tumor representation, and the model's feedback mechanism. From these needs in our initial designs, we developed our top 3 model concepts. With feedback from our professors and peers, as well as the team at the Mayo Clinic, we narrowed it down to our final design concept, which Maité will tell you about now.
Our final model is a functional, anatomically accurate brain model that responds to electrical stimulation. It's a model made out of silicone, and the tumor itself is made out of the same silicone and dyed a slightly darker color to allow for a change in color to identify the tumor and be able to resect it. It's anatomically accurate in the way that it's made, which I'll explain later. And then it also contains electrical components, which is the wiring that you see in the image there, to allow for it to be functional and allowed to mimic that electrical component of the live brain. So the way that our model is currently made is actually taking patient-specific imaging, which you see here, MRI imaging, and bringing it into a software called 3D Slicer to create a volume that we then use to create an inverse shell that we then 3D print. So here you'll see the inverse shell. It's made out of 2 components. The first component holding about 2/3 of the actual brain volume, and then the top component holding about 1/3. And the way that this this shell is created is to allow for it to be successful during its 3D print, but also minimize the amount of actual filament that we are using. So the filament that we use during 3D printing is called PVA. It's a dissolvable polymer, and here you'll see a time lapse of us printing actually the bottom component of the brain shell. And the 3D printing process required a little bit of tinkering with the machine because PVA is typically used as a support since it dissolves in water. However, for our purpose, we needed to use it for the entire body of the entire shell. And so you can see here the actual final 3D printed components of the shell, the left being the bottom portion and the right being the top portion. We then take these components and we place the tumor in it using a small wire that we remove after molding. So you can see that image on the left. We then fill the entire shell with the actual silicone to make the body of the model. We let that set, which takes about 12 hours, and then we place the entire thing in water, and the actual PVA shell dissolves away, leaving us with the final body of the model on the right. We then take that body and using patient tractography imaging, we follow the path that is shown on the imaging and insert the wires and connect it to the final display. And Megan will actually explain a little bit about how the electronics of the device work.
Great. So that electrical component that Maite just described was implemented into our model in order to represent and replicate the function of these corticospinal tracts, specifically for motor cortex, that are to be avoided during any surgical procedure. Normally during surgery, the surgeon would apply current from a handheld electrode probe directly to the cortex of the brain, and nearby motor tracts or other white matter tracts in the brain would be innervated from this stimulation. The extent of this innervation would depend on how far away the electrode is from any of those tracts. So the motor response that they receive from the patient, as well as recording data from the brain, would actually tell the surgeon where they are stimulating in relation to these tracts in the brain. So the way that we accomplished replicating this scenario in our model is with a principle known as electrical coupling, where an electric field will actually induce a current in any nearby conductive object. In this case, our electric fields are actually coming from the brain, specifically from our corticospinal tract representation, which we have in our model as wires, or these gray arrows in our diagram here. The field is generated around these placed wires from a waveform generator, which is coded in MATLAB. So two distinct and distinguishable waveforms are sent through these two wires in our model, and this creates two electric fields within our brain model. So when a neurosurgeon using our device would bring the handheld electrode probe near these fields, a current will actually be induced in their probe, which is detected by the computer connected to the other end. In this computer module, we used a custom analytical algorithm in order to determine which electric field, and therefore which tract, is actually detected by the probe, as well as filter and amplify the signal in order to display it for the user. So while this process doesn't perfectly mimic the electrical conditions and actual neural innervation that you would see during a live surgical procedure, the outcome and the results that we're able to gain from this are the same. So now we have a quick video to actually show you our device in action. So the outcomes that we have from our device are actually shown in this interface for the neurosurgeon. So as you can see, when they bring their probe near the tracts, which are shown by these wires, which we have sticking out of the top just for visualization purposes, the detected signal is shown on these two graphs to the right. So from this detected signal data, we're actually able to distinguish between the two tracts and which of the two wires is being detected based on which signal is stronger, which you can see in the bottom left graph. There are two different signals. Whichever one is taller at the time would indicate which of the tracts they're closest to. This detection works up to about a distance of 5 millimeters, but can be calibrated to include any number of distances. So we're displaying these predictions for the neurosurgeon in the two text boxes that we have. The first one is which tract is predicted to be the closest one, which is determined by whichever signal was stronger. So in our case, we have the left and right leg right now, which are the two wires in the medial portion of the brain. We additionally have a predicted distance as to how far the probe is away from the tract at any given time, up to about 5 millimeters. Along with these predictions, we also have two LEDs that you saw during the video. The first is the orange LED, which turns on whenever a tract is detected. And the second is a red LED that would tell them if they are actually touching the tract itself. So this is a pretty important feature because during surgery, some of this tissue may not be distinguishable by eye, and the electrical responses are actually what is informing the neurosurgeon whether it is safe to cut there or if it would cause permanent damage to the patient. So with all of this feedback that we're providing, we're able to train neurosurgeons and neurosurgical residents to have increased patient safety during surgeries, as well as reduced surgical error, as well as increasing their autonomy in the surgical environment by allowing them to practice these skills outside of the operating room. Like we mentioned before, any engineering project is going to have a lot of testing to make sure that the product meets its original design goals. So two of the goals that we validated here are that there was a quantifiable and reproducible relationship between the electrical amplitude that we detect with our model and the distance between the tract and the probe at any given time. The second goal was whether the material feel of our model is better than the feel of cadaveric tissue, which is the current gold standard for practicing outside of the operating room. So our first test was to measure the relationship between the probe distance from the tract and the detected amplitude that we have from our model. This relationship allows us to predict the distance away that the surgeon is during their training. So to obtain our data, we repeatedly measured the electrical signal at a variety of distances from the tract, as well as very far away to obtain a baseline measurement. So in our case, the baseline is actually very important because our type of measurement, which is just detecting the electrical signal from the environment, is actually very susceptible to electrical noise, which can come from a variety of sources like outlets, lights, and even your computer. So we needed to make sure that the data that we're measuring is actually from the electric fields in the brain and not from the environment. So we see this drop off in our data between our measured data and the baseline, which indicates to us that this is the case and it's not just coming from noise. So after we've ensured that, we fit our data to a linear model in order to evaluate it. So this model had a slope of -1.96 and an R-squared value of 0.86, which indicates that 86% of the variance we see among our data is actually explained by our model. We also created a 95% confidence interval to predict data, and almost all of our data points fall within this bounds, which indicates to us that our device is producing consistent as well as reproducible results. The second test that we did involved comparing the material properties of our model to both live brain tissue, which you would see during surgery, and cadaveric brain tissue, which you would be using to train outside the operating room. So of course, the ideal scenario would be that our model is actually perfectly replicating the feel of live brain tissue, but our goal in designing it was simply to improve upon the feel of cadaveric brain tissue. So the metric that we're using to quantify this comparison is the elastic modulus, or how much the material deforms upon stretching it. For reference, the elasticity of the cadaveric brain tissue is about 140 kilopascals, which is over 9 times the value of live tissue. So it's very different. This vast difference in values is caused by, like Faith said earlier, the fixation of the brain tissue before anyone would practice on it. So this gives the brain a much different feel than you would during a live surgery and is an inaccurate representation of what someone might see during an actual surgical procedure. So our model, by comparison, is only 55 kilopascals. And this gets us closer to the feel of live brain tissue by over 60%. While it's still above the range of live tissue, which only gets up to about 15 kilopascals, the use of this model presents a great improvement upon the current training method of cadaveric dissection. So with the results of this test, as well as our electrical testing, we know that our model was successful in meeting its original design goals. And these validation testing show that the model also presents a much more realistic view of the brain during surgery than training on a cadaver would. We are excited about the potential for incorporating it into surgical training curriculum.
So because we were part of the Mayo Clinic Ventures program, we did want to take a brief moment to address the current market for our product. Each year, there are 13.8 million cases that require invasive brain surgery around the world. Over 660,000 of these cases are located in the US and Canada, and so that is the market that we assessed for our serviceable, accessible market, which is a term that refers to market opportunities that exist within an organization's established core competencies or past performance. So using these values, as well as the average cost of a cadaver and the number of neurosurgeons and neurosurgery residents in the United States, we found a serviceable, accessible market of 15.5 million in the US and Canada. This market assumes a single use, that each user would only use the product one time, and there is a lot of room for expansion and future advancements, which we will discuss in a moment. In addition, we did want to point out the cost savings that are offered by our device. The average cadaver can cost up to $3,000 in the United States, whereas we estimate our product will cost $300 to $400 after manufacturing, which is around a 10 times cost savings. So future advancements, these are 5 ideas that we have thought of to hopefully improve and keep creating new iterations of our model moving forward. First, we would like to incorporate more relevant white matter tracks. So as you guys saw, our current model only includes motor tracks, and this is because we wanted to focus on just excitatory tracks for this first iteration of the model. In the future, we would like to include new tracks for sensory as well as speech function. And these tracks are interesting because they're actually inhibitory. So it poses an interesting challenge for us to actually change the circuitry underlying the device and having both types of tracks coexist in the same model. So we have some exciting ideas about how we could do that moving forward, and it's something we would really like to explore. Next, we would like to simulate the cerebral spinal fluid and blood circulation in the brain. So in our user interviews, we heard from a lot of neurosurgeons that something that's a lot different from practicing on a cadaver to doing a live surgery is how much bleeding there is and actually dealing with the blood flow as well as the different operations of the procedure. So we decided not to look at this last semester just because of time limits, but it's something we would like to explore moving forward. In addition, we would like to improve the simulation of the operating room conditions, primarily through changing the feedback mechanism of our device. So currently our device, as Megan showed us, uses LEDs to show when we are approaching the tracts or whenever we have actually directly hit a tract in the brain. In the future, we would like to change this to an auditory cue, so it is more realistic to hearing instructions from a neuropsychologist during surgery. This will better mimic what it's like to be in the operating room and hopefully better prepare surgeons for listening to this feedback rather than seeing it visually themselves. In addition, we would like to improve the visual display for our device just to make it more clear in the future. Right now, this is just the first draft that we developed for our capstone project, but we think it could be more clear and have better user feedback in the user interface. And finally, this is probably the future advancement we're most excited about, is we would like to expand to patient-specific preoperative planning. So because our device is developed from patient imaging data, we could theoretically develop one for each case that a neurosurgeon has to work on. Not only would this greatly expand our current accessible market, but it would also enable neurosurgeons to actually practice each specific case before going in and doing it inside the operating room.
We are really excited about the value that this product brings to the market and to training in general. It is super exciting that a patient-specific 3D printed physical model can be conveniently created at low cost for surgical planning, procedure rehearsal, patient education, and resident training and evaluation. And deliberate practice using this model will enhance training of not only the neurosurgical trainee, but also the entire team by being able to replicate a multitude of surgical scenarios and improving interdisciplinary communication. But what's really exciting about this model is that it's the first model to simulate direct cortical stimulation and electrical conduction. And these actual components of the model allow the surgeon to be able to delineate between the functional cortex and subcortical tracts and establish the relationship to surrounding brain and lesions, which is super exciting because the simulator actually represents one step closer to a live brain. And this is something that hasn't been done before, which is really cool. Our model in general shows great potential for improving current neurosurgery training methods. Here you can see an image of what the model would look like when being used to approach a glioma. It can be transported safely and easily and used in a variety of different environments. And because it doesn't have biological tissue, there's no need for sterilizing tools or any protective equipment and cleaning. So it makes it a lot more accessible for a wide variety of environments. And as I mentioned earlier, it will benefit not only the neurosurgical trainee, but the entire team. And the addition of the conductivity of the model is a great component and probably the most important advance in the model, and it sets it apart from other simulators that are currently on the market. We're super excited to continue to work on it, and I think that this is a great example of how collaborating between engineering, Georgia Tech, and the Mayo Clinic allows us to implement future iterations and create something as incredible as this. We wanted to acknowledge our team at Georgia Tech from last semester, including Rebecca Forey, our capstone class TA Reagan Newman, and our advisors, Dr. James Stubbs and Professor Rains, for all of their hard work and guidance throughout the semester. We would also like to acknowledge Dr. William Smith for his expertise and advice in the electrical component, and of course, Dr. Q and his team for all of their insight and guidance with everything having to do with neurosurgery. Special thank you to Lisa Norden and Dr. Charles Bruce for their help with the collaboration between Georgia Tech and the Mayo Clinic, and to our financial funding sources for their invaluable support. And we're happy to take any questions.
Beautiful, beautiful work, Brainy Bunch. So would you mind, maybe we can take out the screen so you can see everybody's faces on this beautiful morning. And I see some comments already that are coming through. Dr. Sapsevich, who spent so many years thinking about these issues. So exciting. He couldn't stop texting me right here in the chat privately. Go ahead, David. Take it away.
No, well, guys, amazing work, amazing work. I'm, for those that don't know me, I'm the neuropsychologist that works with the Wake Craney team doing all the mapping. And
David, I didn't tell him to mention the neuropsychology. That was
no,
completely
I
independent of that. All
appreciate
right.
the plug for neuropsych, but I mean, what an amazing training tool. You know, I was talking with Dr. Q when I first heard about this project and got real excited. Where, you know, I envision an OR where you're introducing this model where you have EEG simulations. We pair it with a stealth machine where we import simulated fMRI and DTI data in there. And as you are stimulating, you'll see after discharges appear on the EEG, and we can create algorithms. You know, I mean, we know certain factors increase the risk of after discharges, like number of consecutive stimulations or how high or how long the stimulation duration is and things like that. So we can introduce all this into that model and make it just a real rich and real training opportunity. And the other thing I'll say is that, you know, there's a lot we don't know about the brain and white matter tracks, but, you know, the literature's building, and we can, you know, create these algorithms based on tracks and what functions we believe they're involved with. So when you stimulate a certain tract, you'll see a certain type of error if you're testing for the right kind of thing. So now we introduce sort of this training on, you know, what paradigm should we be using? What should we be looking for? You know, you won't see certain things if you're not doing certain things. I think this is amazing, guys. I'm real excited.
Comments. And the other thing that Dr. Sapsevich mentioned, you know, for all of you is that he thinks that these models can be tested, hypothesis driven per patient, number one, and it can be funded. I mean, this is the kind of work that I serve at the NIH. I just finished my 5-year and the board of scientific counselors. And these are the kind of things that the NIH has been, you know, very, very vigorously looking for things, because the public is demanding this type of care. I mean, no longer can we afford to learn to do brain or spine surgery and learn in our patients. This generation, your generation, one day, God forbid, you or your family member has a brain tumor, you're going to want to have the expertise of someone who's done either many of them or someone who's trained in a different way. And we can no longer afford to train them, you know, in the human brain. So we have to train them before in hypothesis-driven work. It's extraordinary. Go ahead, David.
No, I was just going to say a really interesting study would be just take 5 or 10 low-grade glioma patients. You know, we got some time with the low grade, so we can plan it out. And you take their actual MR data, their actual DTI data, you print a patient-specific model of their brain, and you do the surgery, right? And then some of those patients, and then they go to the operating room and you collect different data like duration of surgery, how many trials of mapping did you have to do to kind of map the surgical field, and you collect all this data, and you also have a group that you don't practice on the model, and you see, and I bet you'll see that the surgeries overall are probably more efficient. There may be a lower complication rate in those that you actually practice on a patient specific model, I think it'd be a nice study to show the value of using this.
And of course, we are advanced in the imaging of the brain, but the same thing can be done in the spinal cord, David, as you recognize in our chat. I have another comment right here by Dr. Fox. Go ahead, Dr. Fox, take it away.
Hey, ladies, amazing work. I mean, as I've said many times before, it's really been inspiring to work with all of you. I think about what I was doing when I was, my first year out of college or my senior year in college, and I compare it to you, and it's a good thing I'm not applying for medical school now because you guys are super impressive. I think many other people probably feel the same. I think, sort of piggybacking on what Dave and Dr. Q just mentioned, the other side of that perspective is how these models can influence the surgeon. Obviously, a lot of what we're talking about is how it makes surgery safer, more precise for the patient, but it also, really helps build confidence, particularly for surgeons who are just starting off in their career, or for residents. Neurosurgery training can be incredibly anxiety provoking, and there's such huge costs if you make a mistake as a trainee. So you think about, the experience of a resident who is able to practice first and then go into the operating room and feel like they've actually been there before and done that before. And those are the experiences that either influence someone to go into, tumor surgery, or say, I don't like this, I want to be a spine surgeon, or vice versa. So I think, and that's a whole nother way to think about studying this from a research perspective going forward, thinking about how this affects, surgeons and their training and how they actually perform. You can measure things like heart rate and respiratory rate, and, with all the monitors that are available today that you can wear on your wrist or your bicep during surgery, you can think about how this influences in a positive way the experience for the surgeon as well. So again, amazing work. It's been great to get to know you guys, and congratulations. It's a wonderful presentation as well.
Thank you, Dr. Fox. I have one comment by Karim, and I can see Dr. Tatum also. I'm going to give the floor to Dr. Tatum. Karim, go ahead.
Yeah, Megan, Maté, and Faith, great job. This is amazing. So I like the concept of the customization per patient, but there are other groups already have done the models, like brain models for anatomical simulation, but for the electrophysiological one, this will be very revolutionary, because as you know, there is something called Brain Box. I'm not sure if you're guys familiar with, and that's a company based out of Italy. They have this a small box. I can share my screen to show you a little bit.
Yeah, why don't you share your screen? Because these are the things that are important. It's different than what our students are doing, but nonetheless, it's important that they know what the space they're competing against.
Yeah, can you guys see my screen?
Yep.
Okay. So you can see here the box is very small, and you can actually customize it for the craniotomy that you want. And that's only for the approach, the anatomical structures, but it's the tractography, it lacks also the electrophysiology, which is, you guys are an expert in that.
And it seems to me that this is a more of an anatomical component, and Karim and I were talking about that last night, but it's important for you guys to be aware of this. You can see it feels more like silicone. I don't think there's any function here, but it's not, nonetheless, it's pretty impressive what they have done. And just looking at the movie, it seems to duplicate what we would see potentially in the operating room.
Yeah, so it's a great job, guys, and this is amazing.
Just for you to be aware. I see Dr. Tatum. He had a comment. Go ahead, Dr. Tatum. He's our epileptologist, just for you guys to know. Go ahead, Dr. Tatum.
Thank you, Dr. Q. Great job, you guys. This is really super exciting. I mean, for an electrophysiologist to see what you guys are doing relative to the monitoring and the changes in the signals that I see, that it's really fantastic. I mean, you know, one of the questions that could be answered by this would be to look at the spatial distribution of the signal. I mean, we insert depth electrodes during surgery, and we could certainly measure them and actually see, rather than an all or none phenomenon on the EEG, we could see a graded response and use that as a predictive value with fluctuating amplitude, how close you are to the tract. So kudos to you. Great job. You know, this is probably the first of multiple experiments. Thanks a lot.
And I think that Maite, Megan, and Faith, I think that what Dr. Tatum alludes to is that having the input also from a electrophysiologist like Dr. Tatum, you know, or, you know, and we had, of course, several of our team members would be crucial. You know, I see Dr. Servin already earlier comment, he's an expert in epilepsy and this type of things, just what he just mentioned right now, this model, just like what you guys did with Dr. Sapsovitz, getting the input from neuropsychology, getting the input from Dr. Middlebrooks and the neuroradiology. These are the ways that these models are made more, even if it's simpler, if it's one type of tumor, yet integration of these things allows you to then test hypotheses in a very, very nice way. Great. Any other comments or any questions from our students, from anybody? Impressive, very, very impressive work. Go ahead, Gabriel, go ahead.
This is many applications just for teaching, for surgery. Good job. And of course, we always love to have these kind of things here in Colombia. It's not that expensive, really. Is a good thing to have before surgery. We always know that planification of something before go to surgery is something that for sure is going to be to do a safe surgery before go to surgery. So in order to do that, of course, include more tracks that you plan could be a better solution in real time for surgeries. Congratulations for you know, for that idea and for continue working on that way. Thank
And
you.
Gabriel, just to give the students a sense how challenging it is in some of our countries in Latin America to get human cadavers to train and to teach, you know, so can you just put it in perspective, because people may not be aware of the challenges
Yes.
that we have in other parts of the world.
As you know, for example, in Colombia, it's prohibited to section a cadaver as in the United States. In the United States, you can buy a brain. In Colombia, it's not allowed. So you have to work in the complete cadaver only in legal medicine, which is completely difficult this time. So it's completely impossible. When we have a course, we need to buy the brains in the United States and bring it to Colombia with many problems, very expensive situation. So this is one thing that really is going to solve this situation. And we can organize a course for electrical stimulation, Dr. Quiñones. We need to think in that, a really practical course and how to do that. Because when we have courses of monitoring, we always have talks without really practice how to do it. So we need to think and develop these kind of things to teach people.
No, and this is what the students alluded to, the fact that not only the brains are hard, you know, when they're fixed, the consistency is completely different, but there's no physiology, there's no function, you know, and this is a way, even though the model, as they said, is simple in the sense that it's one tumor, one location, eventually they can model into anything, but you got to start somewhere to be able to train. One more question, David, go ahead.
No, I was just going to ask for anyone here, what data would we need to 3D print all the vasculature in sort of an accurate way in these patients patients. I mean, I'm just thinking about some of those cavernoma cases we do that are so complex sometimes because of the vessels. And the more real that is, I think, again, the more that the trainee gets out of these simulations. I mean, is it like an MRA? I mean, like what data do you use that would allow the 3D printing to do that? Okay.
So I think this is Maite, Megan, or Faith. You know, the question is vasculature, integrating vascular, especially because what he's talking, the cavernomas are these little tumors that have multiple little vessels coming in, and some of those vessels can be the size a little bit bigger than a hair, but yet they're important in modeling disconnecting them. That's really what, David. So what would you need? A high resolution digital subtraction angiogram or an MRA, or
Yeah.
how do you,
I
I don't know
think
if you had a chance to think about this.
So the way our model is right now is like Maite described, we just kind of have this shell that's the outer surface of the brain, which has all of the, features of the cortical surface, but none of the vasculature that's kind of
Right.
going through. And it's empty right now. So I'm not sure if the current way that we're producing it would actually be able to print all of the vasculature kind of through the model, or if we would have to kind of rethink how we're actually producing it in order to include that.
I think
But
so. I think that,
it's based on the MRI, yes? It's based on the
yes,
MRI of each patient.
correct.
But for
Correct.
for small vessels, you might need a CTA. Is the
Beautiful.
MRA may not give you enough definition for vessels below a millimeter or so. But I think certainly the technology is there, and you could even, as Dr. Q mentioned, do a cerebral arteriogram, and then if you did that stereotactically, you would theoretically have the coordinates to map with a 3D certainty, and then you might have to. I don't know your process as well. I've enjoyed your talk. It's really fantastic work. But you may be able to print out the vasculature and then sort of mold it around. You might have to do this in layers and insert sort of the vessels inside and print the brain around it. I don't know if there's a way to do that.
Yeah, I think that that's a good approach, because the way that it's currently done is we actually fill the shell with silicone. So there's a
Right.
lot of potential for placing things inside before we
Yeah,
actually
that's sort of what I
let the
was thinking.
silicone set. So that
Yeah.
would be a good idea. And then the thought would also be for the fluid, we would want to make sure that it would really mimic, like, the pulsation was something that was mentioned a lot for us. And so we're thinking about like looking at different pumps and stuff like that. That was kind of a thought that we had earlier in the semester that we haven't fully explored yet.
Well, that's certainly, the technology for that is available in that there are pumps used to do vascular simulators. And I think some of that technology could be applied into a CSF sort of model in your model as well. But yeah, I agree with you. I was thinking, looking at your process, it seems like you could place something inside and sort of, as you said, you're filling it around it. You could sort of build it up in layers, and you could include vessels or even ventricular spaces and things as you build it, sort of build it from the inside out.
Dave, does this kind of thing exist for coils, like simulations for some of those intricate vascular surgeries that you're aware?
Yes, it does.
It does. Okay.
We have, there are a couple of simulators that are available, and you can basically, you can even, in certain cases, if you have the cerebral angiogram, you can reprint that sort of, or put it. Some of them are computer based, where you can sort of put the computer model on it, and then you can work with your catheters through. So I think there are some that we certainly make silicone simulator models to train people with coiling techniques and things. And I think there's a lot of marrying that could be done there. This is really, I will echo the many others of us who have been in this field for a long time, who are very, very impressed with what you women have done. It's really great work. You to be
Well, thank
congratulated.
you. This is amazing work. A lot of great ideas. I put a plug in for Lisa because she did mention that, I encourage all of you to submit any ideas you have to our next call for applications. Anything that you guys, I know the team right here, the Brainy Bunch, this is the early stages, as you can see, but it's already amazing. So anything else that we can do to work together on this, incorporating the blood vessels and things like that, the function, the below the cortex as well, that's going to be the next frontier. And we're excited about this. And of course, getting a grant from the NIH, I think there are a lot of requests for applications, and I'll help with guiding some of those things. So thank you, everybody. This is amazing work. And thank you also. You guys should know that there's a patent that they put on this. Our team is just amazing. And of course, there's a manuscript. And it's a really, depending on how this manuscript is pitched, they can go to very high-end journals, as I put in my comments right there. So looking forward to it. And thank you guys for such an amazing discussion and presentation. And we'll have more. And I thank also some of your other colleagues for this, the vertebrals and the no-brainer for joining this morning as well to see what you guys did, because the bar is set high. Very good. Have a great day, everybody. Enjoy your week, okay?
Thank you.
Bye-bye.